Okay, so the last test in class 9 science, chapter 12. Okay, chapter 12. So it is your test 12D. This will cover question number 20, 21, 22, and 28. All this will find on textbook, page 187. So let us start with it. Now in this chapter, sound, chapter 12, we are doing using basically these four formulas, right? When we did the first test, we discussed this one slightly. So let's start with question number 20. Do slowly so we understand it properly. A vibrating body produces a wave of wavelength 2.5 meter. So we can start writing, I think. So here wavelength is denoted by lambda, as we have discussed in the beginning. Wavelength of this wave is 2.5 meter. Meter is the SI unit, so that's fine. And this is your wavelength of the sound wave involved. Then where the wave travels with a velocity or speed, so it's denoted by capital V. So velocity of 1250 meter per second, already in SI unit, meter per second. So this is the velocity of the sound wave. If you want to write full, then you can write. Find this period of vibration. So here, small t here is time as it is normal one. The capital T is the time period of vibration. So you can put that. That's what the question is asking. So time, okay, period of vibration. So with the given values, we choose the right formula. Lambda, capital V, velocity, and T. Lambda Vt. Lambda, capital V here. T. So we're going to use this. So since we know by formula that velocity or speed of sound wave is its wavelength divided by its time period of vibration. So we write that same formula. And we need to find T. So let us just shift this one, V into this T in the denominator will therefore go to the numerator. When you shift from right to left, we're left with lambda. So time period is what they're asking. So T, you keep it on one side, and lambda divided by velocity V. It's just a matter of calculating carefully now. So lambda is here. As you can see, the wavelength value is given up there. 2.5 meter divided by V, the velocity, 1250 meter per second. You can cancel these two, meter and meter. Then 5 is going this with this, so let's just do 5 2s are 10, 11, 12, 2 in hand, 25. 5 5s are 25, no in hand, 5 zeros are 0. So 5 means here also 5 we have to use to cancel. So 2 is less than 5, so put 0 first, then point. Then it becomes 25 on the right of decimal, so 25. So 5 5s are 25. Again, let us do with 5. 5 zeros are 0, point. 5 1s are 5. 5 5s are 25, and 5 zeros are 0. Again, 5 is going, so 5 1s are 5, 5 zeros are 0. Listen to this carefully here. 5 zeros are 0 because we're using 5 to cancel this 50, so we have to use 5 likewise here also. So 5 zeros are 0. Then point. Then after that, 1 is lesser than the number we're using to divide, that is 5. In such case, we know we put 0 first. After we put 0, then we can put 1 0 at the back of 0, and so become 10. 5 2s are 10. So 5 into 0.02 is 0.1. Let me repeat. 5 zeros are 0. Since 1 is less than 5, put 0 first, then 1 0 appear here, 5 2s are 10. So we have here 0.02 by 10. So it's just a matter of doing carefully. Now when you divide decimal numbers like this by zeros, it moves left. When you multiply decimal numbers by 0, decimal move right, but we're dividing, see here, dash by 10. We'll move one place left because of 1 0. So 2 0 decimal was here, but it will go one more place, jump to the left and come here. So it is 0.002. And then here, second to the power minus 1, if we shift to the numerator, it will become second to the power plus 1, which we may not write. So time period is, vibration is 0.002 seconds. So I can write here. Therefore, time period of vibration, as we found out just now, T is equal to 0.002 seconds. This one. That's our answer. Okay. Now let's go to 21. This is done. Now 21. Okay, so let us see that. This slowly, okay. Longitudinal waves travel at the speed of 10 meters per second. So question number 21. Here, speed is denoted by capital V. So at a speed means velocity of 10 meters per second. That is the speed or velocity of the sound wave. In a coiled spring, if the distance between two consecutive rarefactions, is simply wavelength, so lambda is 1 centimeter, is the distance between two successive rarefactions, which means, in other words, it is simply the wavelength of the sound, longitudinal wave involved. So here lambda. Then as we read on the question, find the frequency of the wave. Frequency we know is denoted by lambda. So this is the frequency of the wave that we have to find out. So let us use this, select an appropriate formula involving V lambda. This is frequency is not lambda, sorry. Frequency is small v, sort of small v. V capital is the velocity or speed. V lambda and small v. V lambda and small v here. Number 3, V lambda, this is the one. Number 3, that's how we do our numericals. Select the appropriate formula for that particular numerical we are dealing with. So velocity is equal to V small into lambda, or lambda into small v. Whatever you like to put, lambda into small v. So we know here we have to find this frequency. So just put this small v and then lambda divided by v divided by lambda will come down if we shift. So that way we have here small v equal to, this is capital V is the speed, 10 meters per second, long line, divided by lambda here is the 1 centimeter, 1.0 centimeter. Now we see here this is centimeter, here is meter, means we have to convert the centimeter to meter to put it in its SI unit of wavelength is centimeter. SI unit of length, anything is centimeter. So for that we know the conversion factors that we need to know, as we have discussed even in the beginning, are kilometer, hectometer, decameter, meter, decimeter, centimeter, and millimeter. We know that these are bigger units on the left, and as we go right, it becomes smaller. And we count 1 kilometer, 10 hectometer, 1 hectometer, 10 decameter. If we go from smaller side right to left, 1 millimeter, 1 by 10 centimeter, 1 centimeter, 1 by 10 decimeter, like that we go. Now we need to change this centimeter to meter, which means we're changing small right side to left. So we know big to small, we are multiplying, but small to big, like we're doing smaller centimeter to bigger unit meter, we divide. So we have to divide this one. So here, long line first, then 10 meters per second. Don't touch that. We are occupied with this, right? So 1.0 means same as 1. So you can just write 1, divide, because changing centimeter to meter. So how many places? 1, 2. After centimeter, don't count this. 1, 2. 1 left is 10. 2 left is another 0. So 10 into 10 is 100. So divided by 100 because it shifts 2 places to go from centimeter to meter. Then when you divide by 100, then the centimeter will change to meter. I hope you're getting it right. Then we can see here that will be equal to, and write this one first, 10 meter per second into. So if we change this long line division in the multiplication sign, then up and down. So down denominator 100 will go up, and numerator here 1 meter also. So 1 meter will come down. This meter and meter can cancel. 10 into 100 is 1000 per second, second to the power minus 1. So we know that 1000 per second is this per second, like this, or like this coming to denominator. This or this is same. This is the unit of frequency, hertz. Per second like this or per second like this is called hertz. So we put here Hz, short form of hertz. So per second to the power minus 1 is hertz. Okay, unit, SI unit of frequency. So therefore the frequency that we need to find out here, frequency, which is lambda, is equal to 1000 hertz frequency. Same as the textbook answer. They're using capital Z, sorry. Hertz. I think it's fine, hertz. Okay, so you can write that one. 1000 hertz. Yes, so we can do that one. 22 is done. 21 is done. Now we'll have 2 more. 22. Let us go to 22. So is question number 22 here. Let me read the question. An observer observes the time interval between the sighting of a lightning in the sky. You know that one, right? When we see lightning in the sky, we don't hear the sound immediately. After a few time, we hear the sound. So that means the sound of the thunder from the lightning takes time to reach us. Okay, that's what is happening between the sighting of a lightning and the hearing of the thunder. He finds it to be 5 seconds. So here, time taken is 5 seconds, 5.0. So time taken for the sound from the lightning sound to reach the observer, the person experiencing it. Okay, then if the speed of the sound, speed is denoted by a capital V, so speed of the sound wave is 340 meter per second is the speed of the sound. How far is the cloud from the observer? So that is distance. In this chapter we're using S as the denotation for distance. So this is the distance of cloud from the observer. Cloud means the point where he sees the lightning. We see the lightning breaking out from the cloud, right? So from that point in the cloud, distance of cloud from where lightning is coming out, okay, distance of cloud from the observer. So the observer is standing here, the cloud is there, so the distance between the lightning point on the cloud and him, the observer, that's what we need to find out. Speed, distance, and time is there. So we have to use the formula number 4. We need to find distance S. So let us just use this one. Since distance is equal to speed into time. We know this is a common formula here. Distance equal to this time will go up and multiply speed. Speed into time. So we can replace the values. Distance we're using here as S. Speed we're using as V, time we're using as T, so we can just write it once. Then V here is 340 meter per second, means second to the power minus 1 can be brought down and become plus 1, so meter per second. Into time is here 5 seconds, so 5.0 means we can simply write 5. up and down second cancel. So we're getting here 5 0 0 0, 5 4s are 20, 2 in hand, 5 3s are 15 plus 2 1700 meters. So the distance of the cloud from the observer is 1700 meters. You can write that if you want. Once, therefore, distance of the cloud from the observer, which is denoted by S here, 1700 meters is what we found by calculation. Okay, one more question before we complete this part. This is 28. So question number 28, let us go there. Let me read the question. A sonar device on a submarine means the ship kind of thing under the water that can go underwater, sends a signal and receives an echo 5 seconds later. So this is underwater, let us say. Submarine is here, he sends a signal and maybe hits a cliff in the underwater and the sound has to bounce back and reach. So go there, come here, double distance. So let us do that. So here, T is 5 seconds. So T is 5 seconds is the time taken for signal. Signal here means the sound signal. Signal to reach back. Okay, to reach back the submarine. In other words, a signal is sent from the submarine, so it will go and hit the cliff and come back. So the time taken to go and hit the cliff and reach the submarine from where it came is 5 seconds. Okay, then as we read on, calculate the speed of the sound. So speed is denoted by V here, so we don't know. Speed of the sound means the signal here. Okay, so calculate the speed of the sound in water. Okay, sound in water, that is what we have to calculate. If the distance of the object from the submarine is 3250. Now since in 5 seconds here, this denotes, okay, a sound has to travel twice. Before that you can write here. Okay, just wait 1 minute. Let me do it like this so we understand it properly. Here, okay, since, okay, distance, okay, distance of the object. Of the object means the submarine. Oh no, the cliff kind of thing is object, sorry. Of the object, distance of the object from the submarine, is 3625 meter. Okay, and this is important, and in 5 seconds the sound or the signal has to therefore travel twice the distance between the object and the submarine. I explained already this one, let us repeat once more. Sound is sent from your signal, go and hit the cliff object, let us say is the cliff or a mountain in the underwater, and it will come back. So distance between this and this is 3625, but the distance actually traveled by the sound would be sent from submarine, hit the cliff, come back, so double of this. distance traveled by sound. So let's say S is equal to 3625 meter into 2, therefore double. 2 5s are 10, 2 2s are 4 plus 1 5, 6 are 12, 1 and n, 2 3s are 6 plus 1 7. So this is the distance, total distance traveled by the sound or a signal. So we have here the distance, the speed and the time. So we have to find the speed. Now we know here speed formula. Since we know by formula, write it like this also if you want. Since speed, we know basic formula is distance. Speed is distance divided by time. So we can replace by what denotation we're using in our numerical here. Speed is, we're using v, so we can replace the speed by v is equal to distance, we're using s, time we're using as t, as you can see. And once we're through with that, matter of calculating only, so that will be distance is, the sound goes and comes double this one, not 3625, 7250. So 7250 meter divided by time to travel this much distance is 5 seconds. Simple, 5 1s are 5, 5 1s are 5. 6 7 2 in hand, so it becomes 22 with the next number. 5 4s are 20 is going, 21 22, so 2 remainder goes in front of 5, 25. 5s are 25, then 5 zeros are 0, 1450. That's our meter, sorry, that's our answer. That is find the distance traveled by the sound, distance traveled by the sound. So in other words, finally you can write down total distance or distance traveled by the sound. In this particular case, we have put as S is equal to 1450 meter. Oh, not this distance, they're asking for the speed, right? Sorry, speed. Here, sorry, meter, then this second to the power plus 1 go up, becomes second to the power minus 1, corrected. So speed of the sound wave, speed of the, go back to question, let's use the speed of the sound in water, speed of the sound in water. We are using speed here as capital V. This is nothing but 1450 meter per second. So that concludes our part for Test-12D. Okay, let's go through them sincerely. It's not hard. Okay.